This video is sponsored by CuriosityStream. I thought we'd settled this. Right, me and Mehdi from Electroboom released two videos simultaneously with different explanations for why the chain goes up before it goes down when it leaves a pot. After which it seemed that more people agreed with Mehdi than with me, so I released a follow-up video after which it seemed that more people agreed with me. But did it convince Mehdi?
I watched Steve's video and I thought, damn, I was wrong about this. But then I quickly realized I was just mesmerized with his blue eyes and soothing voice.
This is Mehdi's follow-up video to my follow-up video. And it seems as if now more people agree with Mehdi. So I'm back, and hopefully after this video, it'll be settled and everyone will be persuaded by my explanation. But more importantly, hopefully Mehdi will be persuaded so that we can finally put this thing to bed and I can finally earn my 10,000 Canadian cents. I recommend you watch those past videos if you haven't already. There's a link to the playlist in the description, but you don't have to. I'll summarize here. I believe that for the chain fountain to rise from the pot, there needs to be an additional force coming from the pot. But Mehdi doesn't believe that additional force is required. My understanding of the phenomenon is based on Biggins and Warner's explanation. I'll leave a link to their paper in the description. But the basic principle is that there is some kind of reaction force from the pot. That is to say, as the chain leaves the pot, there is some mechanism by which the chain kicks back against the pile of chain in the pot or against the pot itself. And we know that every action has an equal and opposite reaction, so if the chain is kicking against the pot, then the pot is kicking against the chain, and it's that force that causes the fountain to rise. It may be that there are multiple mechanisms for this kickback force, but I suspect the dominant mechanism is a levering effect. Due to the fact that the chain is somewhat stiff, it can only be bent to a certain point. It has a minimum radius of curvature. So as the chain leaves the pot, this rigid section pivots around its center of mass, causing that downward force on the container. And actually, in the absence of something to push against, you see part of the chain move down. You can see it in this simulation here, and you can see it in this horizontal version of the test where the chain is spaced out. You see, the levering effect causes the chain to move down a little. When the chain is bunched up, you can see that that kickback force causes the pile of chain to recoil. In Mehdi's first video, he showed that a chain fountain can arise in this horizontal version of the test with spaced out chain. And of course, with spaced out chain, there's nothing for the chain to kick against as it's leaving the pile. But I argued that this isn't really a chain fountain, because the peak of the fountain actually recedes. The fact that the distance between the pile of chain and the peak is increasing is just because the pile is receding so quickly. What's interesting is that according to the analysis that I made in the first video, the peak of the chain in this horizontal test shouldn't recede at all. Like, in the absence of the kickback force, the peak should stay where it is. So why does it drop? Well, actually, if you look closely at the analysis, we only expect the shape and position of that arc to stay fixed. In other words, for the chain to move through its shape without the shape changing if the chain is moving in steady state. In other words, if the chain is moving at constant speed and there are no external forces acting on the chain. So actually, we do expect the fountain to recede for two reasons. In the beginning, as the chain is being brought up to speed, well, it's not at constant speed, so we expect the chain to recede then. So we expect the arc not to keep its shape in the beginning. We expect it to recede. But even once the chain has reached constant speed, we still need to think about friction. I suspect that friction will drag the fountain down too. So it's my belief that for the chain fountain to rise, there needs to be an additional force from the pile to overcome friction. And at the very beginning of the test, that force is needed to overcome that downward acceleration we expect due to the fact that the chain isn't yet moving at a constant speed. In my follow-up video, I compare the spaced out case with the bunched up case. And look, in the bunched up case, you can see that the peak of the fountain rises, whereas it doesn't in the spaced out case. Mehdi was quite critical of this comparison, as you can see from this clip, and I actually think he has a point. I think we actually disagree slightly on why my test was bad. Look, let me summarize it from my point of view. In my comparison, the bar for success is set higher for the spaced out chain than for the bunched up chain. Like, if we're saying that the fountain needs to overcome friction, well, look, the distance from the pile to the peak is greater in the spaced out case, so there's more friction for it to overcome, and clearly that's not fair. Mehdi thinks that this comparison actually supports his view of how the chain fountain works. Obviously, we disagree on that, but one thing we can agree on, I think, is the fact that there are too many confounding factors in this comparison. Like, I've changed too many things. In science, you know, if you want to test how one thing affects the other, then you should only really change that one thing and keep everything else the same. But I haven't done that here. You know, in one case there's a kickback force, and in the other case there isn't, but actually in one case the pile recedes more quickly than the other, and so it's not a fair comparison. So what about this setup, where the spacing between the chains is the same in both tests, because I've got these steps here, and the distance between the steps is the same in both cases. But look, in one case, the chain is pressed up against the riser of each step, and in the other case, it's up against the edge of each step. So look, in the left-hand case, there's something for the chain to push against, and in the right-hand case, there isn't. But in every other respect, I think, it's the same. And look, in the case where the chain is at the edge of the step and there's nothing for it to push against, we see once again that the peak of the fountain recedes. But in the case where there is something for the chain to push against, we see that the fountain actually rises. It's interesting that in the case where there's nothing to push against, the peak of the fountain recedes, but only to begin with. Towards the end of the test, it seems as though the peak of the fountain stops receding. And I think I can make sense of that. Like, in the beginning, as the chain speeds up, we expect the fountain to recede due to the fact that the chain isn't in steady state anymore. But once the chain is in steady state, we would expect the chain fountain peak to stay where it is if it weren't for friction. And because of this step setup, we've removed friction from the ground because the chain is essentially flying through the air at this point. And having removed what I imagine is the main source of friction, rubbing against the ground, the peak seems to stay where it is. I also had a look at the effect of damping the kickback force, but first, here's a quick message about the sponsor. I've got this friend who sends me YouTube videos sometimes, and he says, don't worry about the thumbnail and the title, it's a good video, I promise. And he's always right, because he knows me well. And I wish that would happen more often. If you feel that way, then you should check out the sponsor of this video, Curiosity Stream. It's like Netflix for nerds, basically. They've got thousands of movies and TV shows on topics like science, history, nature, food, technology, travel, loads of things. I've just finished watching their Engineering the Future series, and it's really good. Actually, their exclusives and originals are award-winning, but the point is, they're handpicked by experts. They're curated by people who know what they're doing. It's a bit like that friend of mine, but better. Of course, the service is available on desktop and mobile, but it's also now available on your smart TV. The promo on this one's really good. If you use my special URL, curiositystream.com/Steve Mould, you get a whole year for just $14.99. The link is also in the description, so check out Curiosity Stream today. In Mehdi's most recent video, he suggests that the tests where we drop chain from a tray may be inconclusive because even with proper metal bead chain, there seems to be no fountain. But actually that's not true. Look, in this test, the chain reaches a decent height. The fabric is there so we can run the test again, but this time with some really light stuffing underneath the fabric. This stuffing should dampen the kickback force. And actually, look, that's what we see. The chain fountain doesn't rise as much. These two tests, to me, are quite convincing that a kickback force is required. A lot of people suggested that I should try to measure this extra force from the pot. Like if I put the pot on scales, then the kickback force from the chain should push down on the scales, and the weight reading from the scales should be greater than we would expect. So, you could film it, and if you mark the beads so you know how much chain there is in there, but from the marks on the beads, you know how much it should weigh, and you look at the reading and you see what it actually does weigh, and that should tell you the extra force. I actually mentioned in the first video that that's difficult from an instrumentation point of view, like getting scales that are fast enough and accurate enough. But then I thought to myself, you know what, actually, I haven't tried, have I? So this is an extremely accurate force gauge. It samples 1,000 times per second, which should be fast enough. Actually, though, the issue is with the speed of the readout. The readout seems to refresh every 5 seconds, and every time the readout refreshes, it's changed by about 1/4 Newton. Based on my explanation, we actually only expect an additional force from the pot of about 0.1 newtons. That's for a chain fountain height of 30 centimeters. I'll get into the derivation of that 0.1 newtons later. But the point is, every time the display refreshes, it changes by an amount that is substantially greater than the extra force required for the chain fountain to rise, according to my theory. Even worse, there's a delay in the readout of about ½ a second. I mean, maybe if I spent even more money on a force gauge, one that has a USB out that just spits out every one of those 1,000 readouts per second, then maybe I could get something. But even then, I have to worry about that delay and lining it up with the footage on the camera and all that sort of stuff. Basically, it's a really hard problem. But what I can do is use the force gauge in the horizontal experiment and get a reading just at the very end. Here we get a maximum reading of 0.36 newtons, and that's certainly in the right ballpark. In fact, if you look at this version of the experiment, where the chain is presumably going at roughly the same speed because it's also powered by the drill, we get a chain fountain height of, well, a maximum of 1 meter. And according to my theory, actually Biggins and Warner's theory, a chain fountain a meter high requires an additional force of about 0.3 newtons, which correlates really well with the readout we got in this test. But where does that number come from? Why does a chain fountain of around a meter height require an extra force from the pot of around 0.3 newtons? Well, I won't go into the derivation, but using the equations from Biggins and Warner's paper, you get that the extra force required from the pot is equal to the linear density of the chain multiplied by the height of the fountain multiplied by little g. In other words, the weight of this bit of chain. And that makes intuitive sense. If you want to lift a chain that high, you have to work against its weight. 1 meter of this chain has a mass of about 0.03 kilograms. That's a weight of about 0.3 newtons. And so, according to Biggins and Warner and me, that's the force required from the pot to raise a chain fountain of 1 meter. It's also why a chain fountain of 30 centimeters requires about 0.1 newtons, as I mentioned earlier. In Mehdi's follow-up video, he mentions that no one has yet explained why the maximum velocity that the chain reaches is quite low, or at least it's low compared to the terminal velocity of the chain if it was just falling through the sky.
Steve hasn't provided any other reason for this constant speed, like it's nothing.
Actually, that's quite easy to explain, and it has nothing to do with the chain fountain. It's possible to derive the maximum speed of any chain falling from a pile, whether there's a fountain effect or not. Consider the setup where there's already a long piece of chain dangling. That length of chain feels a force downwards from gravity, but there's another force resisting that motion. The force is provided by the inertia of the chain that is being pulled from the pile. In other words, the chain in the pile resists being pulled into motion. And that makes sense. Like, we tend to think of force as mass times acceleration, and that's true, but force is also just the rate of change of momentum. So the fact that momentum is being imparted into the chain that is pulled from the pile, that requires a force. And that force is provided by the chain being pulled down by gravity. In the beginning, those forces are unbalanced, so the chain accelerates. But as the chain increases in speed, every new bit of chain that leaves the pile is imparted with more and more momentum, because it's leaving with more and more speed. And so the inertia of the chain in the pile provides a greater and greater opposing force to the chain falling under gravity. Eventually, at a certain speed, the force required to bring the chain from the pile to that speed matches the force of gravity pulling down on the dangling chain. And that is the maximum speed of the chain. It falls out of the maths that that speed is equal to the square root of the height of the chain drop multiplied by g. Towards the end of Mehdi's most recent video, he shows this brilliant demonstration from Peter Steinkamp of a chain fountain rising from a chain that is draped over a rod. And that's really remarkable because clearly there's a chain fountain and clearly, to me at least, there's no lever mechanism. So this shows a chain fountain without a lever mechanism. So does this prove me wrong? Well, as you might imagine, I don't think it does. I think that for the chain fountain to rise, there needs to be an additional force from the pot, or in this case, there needs to be an additional force from the rod. In the case of a chain rising from a pot, I think that force mostly comes from the lever mechanism, which I talked about earlier. If you want more details on that, by the way, I talk about it more in the previous 2 videos. But in the case of the rod, I think there is still an extra force, but I don't think it's from the lever effect. I think it's from, well, if I had to give it a name, I would say the pulley mechanism. This is just my first guess at what's going on, but look what happens here. As this chain moves up, this loop also moves up, and that makes intuitive sense. That's the behavior that we would expect. But as we've seen before, eventually the chain will start to flow through the loop as well as the loop moving up. Like here, when I pull on the end of this chain, the loop moves up, but also the chain starts to flow through the loop. Let's lay this out on the floor so we can see what's going on a bit more easily. So, right, imagine this is up and this is down. Here's the pipe. So initially, as this chain is moving up, this loop proceeds, but then it starts to flow through the loop as well. So this bit of chain starts to pull down. Obviously, if this pipe wasn't here, then you would get the same thing happening again. You know, this loop would recede as this bit of chain moves down, but it can't because the rod is in the way. So the rod feels an additional downward force from the chain, and every action has an equal and opposite reaction. So the rod pushes back up on the chain. And what's great is you can see it in action. Look, this bit of chain here, before it's even that bit of chain's turn to start moving, it's already moving upwards a bit. And this additional upward motion each time adds up. And so the chain fountain grows. You might say, well, hold on, the force pulling on this bit of chain isn't coming from the rod, it's coming from this bit of chain. And there's a sense in which that's right. Like this downward force is being redirected into an upward force on this bit of chain. But you can't just redirect a force. Like in mechanics, all the forces have to balance. A downward force can't just become an upward force. In other words, it's the upward force from the rod that does the redirecting. And if you study dynamic problems in pulleys, that's the kind of balancing you would do. And so I believe that if you were to remove the force from the rod, then the fountain would disappear. You can remove the force from the rod by removing the rod, but as in previous videos, you can't do that on Earth because it would all just fall down under gravity. It's another good candidate for an experiment to do on the International Space Station. But in the absence of that, we can once again run a simulation. It's interesting that Mehdi didn't mention the simulations in my previous video in his most recent video. Why didn't you mention the simulations, Mehdi? Why didn't you mention the simulations? With the rod in place, the simulation does indeed produce a chain fountain. But look, when you remove the rod, but also turn off gravity in the red rectangle, the fountain disappears. Thanks again to Martin Barth for these simulations, and that's it for this video. Was it enough to convince you? More importantly, was it enough to convince Mehdi? It all makes sense, Mehdi. It all makes sense. Trying to figure out the explanation for a phenomenon in this adversarial way has been really enlightening. Like with that horizontal comparison test that I was doing with the spaced out chain and the bunched up chain, I thought that was good. And you know, it's important in science to try and look for the ways in which you're wrong. And I thought I was good at that, for looking for my own mistakes. But clearly, I'm just not as motivated to find mistakes in that stuff as Mehdi is. And that's thanks to the adversarial way that we're doing it. So that's a really good lesson that I've learned from Mehdi. And of course, I've learned loads of really great lessons, mostly about electrical engineering from Mehdi's channel, Electro Boom. I'm sure by now you've checked it out, but if you haven't, you really must. His videos are great. The link is in the description, but it's also on screen now. I hope you enjoyed this video. If you did, don't forget to hit subscribe, and the algorithm thinks you'll enjoy this video next.